Okay, you're good to go.
Good. All right. So thanks everybody for joining. This is the Friday panel session of the Symposium about fundamental physics and waveforms. So my name is Stefan Massa from Explorative Tools. With Professor Martin Amory, I will be chairing this session. Right. So just to give you the list of speakers that we're going to have today, we're going to have Anson Chen, then Yannis Nolla, then Chantal Pitt, then we have a 15 minutes break. Then Lorena Magana Satucci, Massimo Vaglio, Pankaj Saini, and Giovanni Maria Tomaselli. I apologize in advance if I mispronounce your names, please. And the way the session is going to work is that you can ask questions in the chat at any time. We'll keep the questions for the end of the presentation. You can also raise your hand if you want to ask your questions directly. Questions can also be asked in the chat of the YouTube live stream, and we will read them for you. All right. So I think we're going to start with the first presentation. And Son, if you want to share your screen.
Yeah.
So the first speaker, yeah, we can see the screen. Right, so the first speaker is Anson Chen from Queen Mary University of London, and he's going to talk about measuring the propagation speed of gravitational waves with LISA. So I forgot to say the duration of the presentation is 15 minutes, and I will give you a cue 3 minutes before the end so that you know about the time. All right, the floor is yours.
Yeah, apologies. I need to stop sharing now and share again. I do see the full screen.
Yeah. We see the screen now.
Is it full screen?
No, it's not full screen.
Okay, there's a little problem here, and apologies, my camera doesn't work at the moment, so bear with me. I'm trying to restart these slides. And share again.
So we still see your screen, but not full screen.
Yes, so but it cannot be start full screen. So weird.
It did work a few minutes ago.
Oh, is it working?
I mean, not when we tried before, right?
Yeah. Yeah. Can I join the Zoom again? I just leave for now.
Yes. I mean,
okay,
you could also show in.
Right. Quickly.
Okay, slight technical difficulties. We did have this working about 15 minutes ago, or this is the challenge of all the different formats people use, and Anson, I believe, is going from Ubuntu. He's not playing with Zoom today.
Hi, I'm back.
You're back?
Yeah, audio is good.
Try again. How about it?
Yeah,
perfect.
That works.
Great.
All right.
So sorry about that. So yeah, I'm Anson Chen from Queen Mary University of London. So I'm talking about measuring the propagation speed of gravitational waves with LISA. Yeah, you can find the works on archives. So here are all the people working together in the cosmology working group of LISA. Okay, so let's start with the motivations. So we know that we have a constraint on the gravitational wave speed by this binary neutron star events. with electromagnetic counterparts. This constraint is very tight, so the deviation of CT, the gravitational wave speed from C, is smaller than 10 to the minus 15. However, there's a caveat that this measurement happens at the merger of BNS, which is in the order of 1,000 Hertz, but we don't have data now to constrain the GW speed at a low frequency scale. So it could be that some physics happen where CT travels slower than C. So here is an interesting model. It's an effective field theory model of dark energy. So there's an operator in the action that predicts a scale that is called a UV cutoff. So at a high energy scale, larger than the cutoff, then gravity follows general relativity. But at lower energy scale, corresponding to low frequencies, so there's a coupling field to the gravity that makes the CT travel slower than the speed of light. So as we know, we can detect massive black hole mergers at laser bands. So it is a good indicator for us to test the theory of gravity here. Okay, so let's start with theoretical framework. So we write down GW propagation equation. So when CT is 1, then it is the GR propagation equation. So now CT is smaller than 1. So we find that the CT modify both amplitude and phase of the waveform. So we can separate them and study amplitude and waveform. So the most important things that has been changed in when introducing CT is an extra factor of CT in the relation of frequency in observer and the source frame. So it will lead to the difference in the waveform. So if we take the derivatives with respect to the frequency, with respect to time, then we can find an extra factors here. So it is some combination of delta, which is 1 minus the ratio of CT in observer frame and the source frame. So there's a delta and the frequency derivatives of delta. And this is the usual redshift relation. So we can integrate the inverse of these derivatives and get time before merger, and integrating it again, we can find a phase. So here's how we find a phase. So here we include post-Newtonian expansion up to 2.5 PM order. And we also find the modification to the amplitude. So this is the gravitational wave luminosity distance. So it is the usual luminosity distance multiplied by also an extra factors depending on CT. And replacing the luminosity distance by the gravitational wave luminosity distance, we have this usual GR combination with MO to be the observed chirp mass. And there's also an extra factors of this ratio in CT. So here we consider only the propagation effects on the waveform, and there's now there is no model, waveform model for modified gravity yet. So we don't know what happens at merger and ring down. So, but we assume that it can be modified in the same propagation effect here. But to be conservative, we here only show the Fisher matrix forecast with in spiral waveform only later. So let's look at the end source of CT. So first we use a polynomial end source, which is an expansion of CT in a series of frequencies. So here F over F star is a small number. So F star is a frequency scale outside this band. So we have this small number. So when F star is higher than laser band, then we have the positive power. And when in when f star is lower than laser band, we have negative power. So this is always more. So beta 1 and beta 2 controls the deviation. And the second one is EFT-induced source, which is a Fourier-based model. I saw it in the motivation. So it is a more complicated form, but it also have a frequency scale f star here. But this is within the laser band, so CT transits within laser band. So here is a more direct image for this formula. So we see a transition happening around the scale of f star. So C0 is a constant values at the low frequencies. So CT is a constant lower than speed of light here. So after transition, it become 1. So here is a plot of delta, which is 1 minus this ratio of CT. So we see it is zeros on both sides because CT is constant here. So it goes through peak values when the transition happens. So let's look at how the waveform is modified in the plots. So we take the negative polynomial k as an example here. So we take some exaggerated values to visualize the effect. So the power is negative, so it means f star is lower than laser band. So let's look at the amplitude plot first. So we can see a deviation between the modified waveform and the GR waveform here. So the black curve is the noise curve of laser. So we can see the deviation become larger at the low frequencies because it is closer to f star. So we can see a lower, the higher mass system can show a larger deviation here because it has a lower frequency. So it's similar in the phase. So the phase expression in a Poisson-Newtonian expansion looks like this, and the correction and modification comes into the factors here. So we can see a similar features at low frequency. The deviation is larger. So we perform Fisher forecast to the waveform. So we're still using this example. So we'll estimate the parameters of redshifted chirp mass, the symmetric mass ratio, redshift, and TCM size C are Newton parameters in the phase, and beta 1, beta 2. So we assume 30 days of observation before merger. So here is a selected contour for some parameters. So we can see the chirp mass and the redshift. They have a good constraint here. And look at beta 1, we have a constraint in the order of 1. It is decent. But we have a weaker constraint in beta 2. It's a few hundreds. So this is likely due to the second order terms. It is quite a small number. So we make it difficult to constrain beta 2. So this is also why we only stop at order of 2, because the constraint will be much weaker if we expand to higher order. And we also observe some high degeneracies here. This could be due to these parameters. They are all appear in the phase. So it is, they are quite degenerate. We also compare the Fisher forecast with MCMC simulation results. So we take a system of this, and it has an SNR signal to noise ratio about 1000. So it's a quite high SNR. So we can see they agree quite well, the Fisher forecast and the MCMC. And yeah, we find good agreement. And in a lower SNR case, the constraint, the level of constraint is generally the same, but we can see a shift in the for MCMC, the center of the contour will shift a little because it has a low SNR, but in general, it shows that our Fisher forecast is quite robust comparing to MCMC results. Okay, here's a plot to show you the constraint on beta 1 on top of the SNR contour in red in a parameter space of total mass and redshift. So it means, yeah, the different system with the total mass and different redshift will give us a different constraint. So we can see the constraint goes from 100 down to 1 across the space. So we can see a good constraint will come from system with 10 to the 5 solar masses, and lower the redshift, the better the results. Yeah, we can see it generally follow the SNR contour here. And we also show the peaks of the massive black hole population in 3 models: POP3, Q3 no delay, and Q3 delay. So the POP3 model predicts a lower mass massive black holes. So it will give up a bad constraint if the model the population follow the model. But if the population follow Q3 models, we have more events taking place within this region, so it can give us more sources to make our constraint better.
And so just to say you have a few minutes left.
Yeah, thanks. So yeah, if we can combine multiple sources in all the 3 models. So here is some population density across this total mass and redshift space. So it shows you some population density. We can see Q3 model, most of the massive black hole population has a medium range total mass. So when we combine all the Fisher constraints together, we find that the constraint on the beta 1 or beta 2 values is as good as the one from one golden source, which means if we have multiple sources and combine together, even we don't detect the best constraints from one source, we can still get a decent constraint from multiple sources. Right, so at last I will talk about EFT induced case. So let's remind you the complicated formula here. So if we look at a plot, we can see similar features as the polynomial case. So if we take a transition at around 10 to the minus 4 Hz, then we can see before the transition, the waveform is different from GR, but after the transition, because CT become 1 again, so yeah, it's the GR waveform here. So similarly, the base show the similar features here. So if we look at the plots of the constraint on C node and F star, we can find the constraint, the order of constraint is quite good for C node and F star here. So C node error in C node is just about 10 to the minus 4 for the best case. And the relative error on F star is 1%. So these are quite good for the system with mass of around 4.5 solar masses. So we can see the best constraint shifted a little from the SNR contour. So this means actually the transition take place in important parts. So if the transition take place just in the middle of the in spiral stage of the waveform, and the waveform is inside the laser band, then because this in spiral stage will stay for a long time, so it will give us much information about the waveform, so it can give us a better constraint on these parameters. Okay, great. Let me summarize. So our work established tests of GR in weak field limits with gravitational waves. So it will extend the constraint on CT to low frequencies. So we introduced two answers for CT with two modified gravity parameters, beta 1, beta 2, and C0 and F star for polynomial case and EFT induced case. So a typical constraint on the beta 1 in polynomial case for a typical system of 10 to the 6 solar masses at redshift 1 is in the order of 1, but we get a weaker constraint on another parameters, beta 2. And finally, in the EFT case, we find that the C0 and F star can be constrained quite well if the transition of CT happens in the laser bands, but if it would get worse if the F star transits outside laser band or close to the bounds of the laser band. Yeah, that's what I want to talk about. Thank you very much.
Thank you very much, Hanson, for this very interesting talk. So we're a bit over time, but we started a bit late due to technical difficulties. So I don't know if the audience has questions. You can either raise your hand or type them in the chat. I don't see a question for now. So I have one myself. I think you said it, but I did not fully catch it. To what extent is modification, does a modification appears as a modification of PN coefficients, and to what extent does it create really new terms?
Yeah. So we find that all the correction is in the known PN orders. So yeah, in some cases, for example, in the negative polynomial cases, it could appear the lower PN orders, which is lower than 0, which is not appear in GR. So yeah, it creates some new post-Newtonian terms, and it actually can help us to constrain the models, because new PM orders would be a big change in the waveform. So is it
okay? I see. So the structure is actually changed. It's not only modification of existing contributions. Okay.
Yeah, yes.
I see. Okay. If there is no more, there are no other questions, I think we can move on. And thank you again, Hanson, for this talk.
Thank you.
So Janos, if you want to share your screen.
Sure. Let's see whether I have better luck with the technical side. How is that looking?
Good. We see your screen, your slides in full screen. So
perfect.
This is the next talk. It's going to be by Yannis Nola from the University of Portsmouth and the University of Cambridge. And it's going to be about probably the speed of gravity with LBK, LISA, and giant observations. The floor is yours. You have 50 minutes, so we give you a cue at -1 minute.
Perfect. Thanks a lot, Silva. And thank you for the introduction. Thank you for having me. And especially also thanks to everyone for being here on the last day of the workshop. So I'm kind of in a very privileged position here in that Hanson has perfectly set the scene also for my talk, as you heard from Silva. I'll be talking about also probing the speed of gravity, but on a slightly wider frequency range. So both considering observations and forecasts for the LIGO-Virgo-Cagra band, the LISA band, and also intermediate frequencies, so joint observations. And the majority of what I'll talk about is, I don't know whether you can see my mouse, is in this paper here with Ian Harry from the ICG in Portsmouth. And you can find more information in this archive identifier here. So I would like to start by, I guess, expanding a little bit on what Hanson said in terms of the motivation, and really reminding you why this is interesting in the first place. So like Hanson said, of course, we already have exquisite constraints on the speed of gravity, on the speed of gravitational waves from about 5 years ago, GW 1708-17, binary neutron star merger. We got these exquisite constraints at the level of 1 part in 10 to the 15 on the speed of gravity. But one important assumption that went into these constraints is indeed assuming that the speed is frequency independent. So in terms of the plot you're seeing here, where I plot the speed of gravitational waves versus frequency, this would just be some horizontal line. It would have to be very close to the speed of light, given the constraints from GW 1708-17. But what kind of answers already motivated, what I'll try to convince you of and give you a little bit more intuition about here is that actually for the kind of theories of interest here, namely the ones where the speed of gravity in principle is different from the speed of light, especially at low frequencies, so to the left in this plot, it's very natural for this to be frequency dependent. And so to get a transition that looks a little bit more like this. Now, your knee-jerk reaction to this may be that you feel that this looks like you're bending over backwards to satisfy the bound from GW 1708-17 and to create some interesting phenomenology, pull it out of a hat for lower frequencies. But what I really want to emphasize is that this is actually very, very natural in these kind of theories. And so let me try to give you a little bit of intuition here. One of the main motivations for considering different speeds of gravitational waves at low frequencies are these dark energy theories. And there's a big class of them where the speed is indeed different from the speed of light. And generically, what happens there is that at very low frequencies, in fact, the speed can be different from the speed of light, but again, it is frequency independent. So you recover this sort of asymptotic horizontal line at low frequencies, which can be offset from the speed of light. But as you move closer to the LVK band, there's a special scale in this theories, and the special scale is a little bit like the Planck scale in general relativity, where in general relativity, the Planck scale tells you lots of things, but one of the things it tells you is where the theory breaks down. You know that once you approach energies which are close to the Planck mass, the theory becomes non-unitary, it becomes ill-defined, and you need some new physics to come in to save the day. And this is, of course, the infamous search for quantum gravity. So in these dark energy theories, there's different coupling constants, different scales. And it so happens that the analog of this scale sits in the LVK band. And if you convert that energy scale to a frequency, it sits at around 10 to the 2 hertz. And so just as in the GR story with the Planck mass, you know that some new physics needs to come in around 10 to the 2 hertz for these dark energy theories to save the day and to make sure that they become wholesome again. And so, of course, we don't really know what this new physics is, just like we don't know what the true theory of quantum gravity is in the GR context. But there's a sort of very fundamental intuition you can have. If this new physics is Lorentz invariant at a fundamental level, and the solutions are Lorentz invariant too, then that will naturally lead to the speed of gravitational waves transitioning back to the speed of light. And so this kind of picture you're seeing here is a very generic and natural picture in dark energy theories that affect the speed of gravitational waves at all at lower frequencies. So this is kind of the basic intuition why this is not just something to cook up to have something interesting for phenomenology, but it's really something that's fundamentally very well motivated. And there's this nice paper that I'm highlighting at the bottom here by Claudia and Scott that kind of tells the beautiful story behind this. Okay, so we would like to constrain these kind of frequency-dependent speeds of gravitational waves. And of course, we need some kind of ansatz. You already saw some examples in the previous talk. That parameterizes this, some parameterization for the speed. And so we're coming up with something here that has, again, quite a beautiful story hiding behind it in terms of the link to the underlying fundamental physics. I'll cut that short here in the interest of time and just give you the answer that parameterizes the speed of gravitational waves here. And you can see it's this ansatz at the very bottom, which only has 3 constant parameters. The first one, this delta CGW, is basically telling you what the step size is, what the offset is between the asymptotic speed of light at high frequencies and this asymptotic speed of gravitational waves that's different at low frequencies, so the cosmological motivated one. Second parameter is F star. Again, it's a parameter you saw in the previous talk as well, which is the kind of the frequency where this transition takes place. In terms of the fundamental physics, this corresponds to the energy scale where the new physics is coming in that causes this transition. And finally, there's a sigma parameter, which basically in terms of the template tells you about the steepness of this transition, how quickly it takes place. And again, this encapsulates a lot of the underlying physics from whatever new physics is causing this transition. So you have this fairly simple 3-parameter template, and now we would like to confront this both with data from LIGO and with forecasts from LISA and similar observations. Okay, so before actually confronting this with the data, I want to just take one moment to think a little bit about what kind of physics is actually driving these constraints. And I want to tell you this with a very simple example. So suppose we have some frequency-dependent transition, a little bit like in the top left corner here, where the speed of gravity increases with frequency, some lower value at low frequencies, and then goes to some higher value as you go to higher frequencies. Now, think of some typical compact source that you may see in LISA or LIGO Virgo Cagra or a similar detector. Of course, the source is not monochromatic, but what really happens is that earlier on in the in-spiral, you get signals that of a lower frequency, and later on in the in-spiral, the frequency increases, the pitch goes up, and we get higher frequency signals. So with the frequency-dependent transition of the speed of gravitational waves, what will happen is the signals that are sent out earliest are traveling slower than the signals that are sent out later on when the frequency of the wave is increased. And you can get into this, well, funny, if you like, situation really, where the speed difference is large enough that the signal parts that are emitted later on in the in-spiral are actually catching up and in principle overtaking the earlier part of the signal on the way to the observer. So in principle, you can get a situation where at the observer, you actually see the merger before you see the in-spiral. Now, of course, that's a drastic example, but just from this kind of back of the envelope calculation, just to give you some intuition for a source that sits at around 400 megaparsec or so, just a shift in the speed of gravitational wave by around 1 part in 10 to the 9 shifts the signal by over a year. So once we get to shifts by 10 to the -8 or so, that's really something you can constrain just from the fact that you see mergers before you see the in-spiral. And of course, we can do much better in terms of gravitational wave analysis. We can work to much higher precision than this. But just to give you some intuition about the underlying physics that drives a lot of these constraints. There's many other different types of effects that you can also take into account and use to constrain the speed of gravitational waves and their frequency dependence. But this is the one we find to be the most constraining in the cases we look at. Okay, so let's first look at real data constraints from the LIGO band. And so I want to start by sort of looking at a simplified example where we have a transition a little bit like this here, where it's just the very tail of the transition that kind of leaks into the LVK band. And in that case, we can simplify the template and we just have the difference in the speed of the gravitational wave from the speed of light at some reference frequency and then some fall off with the frequency as we approach the speed of light. So this is kind of a simplified version of the template that just comes out of a Taylor expansion in that tail. Now we can run a full Bayesian inference code with the data from GW 1708-17. And you see kind of all the different points that are accepted in running this inference code here for evaluating the difference in the speed of gravitational waves from the speed of light at a reference frequency of 30 Hertz, and for different values of this steepness parameter, this power law parameter. And so you immediately see that just from this one observation, GW 1708-17, we can bound the speed depending a little bit on the steepness parameter, but roughly at an order of 10 to the -17 or better for higher powers of sigma here. And so that immediately tells you that even for mild frequency dependence, you immediately get significantly stronger bounds than for a purely frequency independent speed, where the bound was around 10 to the -15 in the case of GW 1708-17. We can also do something which is a little bit more analytical and which will be useful for the forecasts, which is instead of running the full Bayesian inference, which we can do when we actually have data, we just approximate the exclusion capability that we have. And we can do that by computing this so-called distinguishability criterion here. The experts in the audience will recognize this as a noise-weighted inner product from the residual of the parameters here. But the people that maybe for whom that's not so familiar, I can give you a little bit of intuition about what's happening here. Really, what you're doing fundamentally is you're taking some fiducial waveform, some general relativity waveform, and now you're kind of dialing up this modified gravity parameter, in this case, the deviation of the speed of gravitational waves from the speed of light. And you keep dialing it up to the point where you find that the waveform has morphed so much that with the detector sensitivities that you have for a given detector, you can tell it apart. And so the line in this plot that kind of corresponds to what we have on the right is the top line here. That's also for a reference frequency of around 30 Hertz and for the advanced LIGO detector. And you see that this exclusion line here lines up relatively well with the exclusion from the data. with a little difference, namely that this here is about 1 to 2 orders of magnitude too optimistic, which is not so surprising because this way of estimating the exclusion capability ignores any correlations between the different parameters that this full Bayesian inference model takes into account. But the point I want you to take away is that this kind of approximate exclusion capability is getting the ballpark right in comparison with the real data comparison. Very good. Okay, so until now, I've kind of given you the simplified template where we're just working in detail. Now let's really go to the full template. And I'm plotting the results in a slightly different way here. I'm plotting a parameter space where on the y-axis, we have the steepness parameter. Here we have the central or the reference frequency. Sorry, not the reference frequency, just the central frequency associated with this transition here. And in this color plot here, I'm basically telling you at different points in this plot how well we can exclude, to what level we can exclude deviations in the speed of gravitational waves from the speed of light. The contour lines correspond to 1 part in 10 to the -3, -6, -9, -12, and -15. And this here, I'm focusing on frequencies just in the bottom of the LIGO band, all the way to a little bit below the LISA band here. This is what you get just from a single observation of a GW 1708-17-like event in the LIGO band. And something that you see...
I'm sorry, you have a few minutes left.
Okay, I'll need to speed up a little bit, but thank you, Sylvain. Something that you see that's very powerful already is just from this single observation in the LIGO band, you find very strong constraints all the way deep into the LISA band for sufficiently slow transitions. Now we can run a similar case for just a collision of supermassive black holes in the LISA band. Again, just a single event, one of these golden events, as Anson was calling them. And again, you see that deep in the LISA band, we get constraints up to 1 part in 10 to the 17 or better. So very, very strong constraints, again, just from a single source. And finally, we can just put these two events together, and we get this constraint here, which massively constrains the speed of gravitational waves all through the LISA band and a little bit below and above. And of course, I'm just cutting out the LIGO band because, as we saw before from the data, that's already very, very strongly constrained. Okay, so let me speed up a little bit just so Silvana doesn't shout at me. The one thing we can do here is we can also, instead of doing this for LVK and LIGO, we can forecast how this would work for something like the Einstein telescope. And so you can see that the bound on the left, the GW 1708-17-like observation, that gets tightened as I go to the Einstein telescope. And similarly, on the very right, we even further squeeze this parameter space and find these constraints, even stronger constraints on the speed of gravitational waves. Okay, now the final point I want to make in the last 2 minutes or so that I have is that there's kind of this plot is fantastic and really nice. It gives us very, very strong constraints on the speed of gravitational waves in the space of parameters. But there's sort of a sore spot, which is this top right corner here, which corresponds to very sharp transitions where the sigma parameter is quite large. That happen at around 1 Hertz. So just in the sweet spot between the LISA and LIGO bands, so that observations there can't constrain it very, very well. And a complementary way of constraining this is looking at multi-band constraints. So this is sources like GW 1509-14, which corresponds to this black line here, which are in principle visible in the LISA band and later on in the LIGO band. And there, one thing you can do is you can very accurately predict from the observations in the LISA band when they will arrive in the LVK band. And you can do that roughly with an accuracy of around 10 to the 5 seconds, or in human units, this is around a time scale of a day or so. And so that means that if you don't see the event at that time, that's kind of a smoking gun signature for something interesting having happened here, a transition in the speed of gravitational waves in this island that was unconstrained previously. And so that means for a source like GW 1509-14 to be detectable in the future, these multi-band constraints can in principle constrain this delta CGW up to 1 part in 10 to the 12. Okay. I will skip this slide here just so that we have a little bit of time for questions, hopefully. And I'll just go straight to the conclusion slide. So just let me emphasize, number one, we can actually constrain these deviations in the speed of gravitational waves very, very tightly already with single golden observations in the LVK and LISA bands. There's some small region of parameter space that's unconstrained by this and very interesting also for future observations like EDGE or so. And we can also constrain that very tightly with multi-band observations. And finally, you should really think of these kind of frequency-dependent transitions as something very well motivated from underlying fundamental physics. So in some sense, watch this space for when more and more observations come around. Hopefully, we'll learn much more about the underlying physics in the process as well. Thank you so much.
Thank you very much, Linus. It was a very nice talk. It was a nice synergy between the first two talks, I find. So we have a little bit of time for questions. I haven't seen any question in the chat so far. There is one from Jemison. Go ahead.
Mm-hmm.
Hi, Johannes.
Hey,
just a question about redshift. Did you include the redshift, and what is its role? What do you think it is, the role of the redshift? Because you talk about supermassive black hole binaries that could be at high redshift.
Yeah, that's
so
right.
In all your idea, in all your approach, what's the role of the redshift in your opinion?
Yeah, so for the one thing I should say maybe up front is, of course, the plots I'm showing here are kind of for just a single event in the LIGO band or in the LISA band. So that's something that make it improved with more events. For the redshift, so here we're really considering supermassive black hole, a binary merger where the masses are roughly 10 to the 6 solar masses, so something like Sagittarius A. And if I remember this correctly, we placed them at a redshift of 0.1. So that was the redshift that we had there for that representative event. If you move the redshift around, of course, that can modify the constraints a little bit. But here we're really thinking of order of magnitude constraints. So I guess even if it's a little bit further away or so, or a little bit closer, I'd be surprised if that changes things dramatically. I think the order of magnitude is really what stands here.
Okay, thanks.
All right. I cannot see another question, but I will have one myself. Actually, could you comment on is there any modification to the two-body problem itself and to the evolution of the dynamics of the binary to be considered when you consider these theoretical modifications? Or is it a pure propagation effect?
Right, so that's an excellent question, actually. So in principle, there's lots of different effects, right? So you may have spotted that really the effect behind the constraints that Anson was talking about and that I was talking about, that's different types of propagation effects. But there is really also other further effects that you may use. And so one thing that we looked at early on is really something that's an intrinsic source effect, if you like. So for example, the fact that the speed of gravitational waves is different, that does leave an imprint on the power emitted in the binary in the first place, for example. And you can also use that to place constraints, but they are much weaker than what you have here. They're at the level of 10 to the minus 2, maybe if you push it 10 to the minus 3. So I guess it's one thing that I guess is a challenge in all of these things is thinking of all the possible effects and some phenomenology like this could have, which is lots. And then you sort of need to hierarchically order them in terms of what gives you the strongest constraint. So yes, but at least the ones that we could think of are systematically weaker than this kind of propagation effect in terms of bounds.
All right, thank you. If there is no other question, I think we can thank Johannes again for this interesting talk and move on to the next speaker.
Thank you very much.
Chantal, if you want to share the screen. So we see your video. Do you want to share your screen?
Yes. Okay, can you see it full screen?
Yes.
Okay.
Right. So Chantal Pitt is from CA in France, is gonna talk about the detectability of modes with LISA. So you have 15 minutes, and I will tell you 3 minutes in advance before the end.
Okay. Okay, thank you very much. Well, yeah, first of all, thank you for having me. This is my first conference, so I will try to do my best. So yes, my name is Chantal Pitt. I'm a first year PhD student at CEA-Saclay and also in association with Université Paris-Saclay. And today I'm going to give you some insight on the detectability of modes with LISA, which is work I carry on with these collaborators shown here. So, sorry, I cannot move. Yeah. So I will start first with my motivation, and this is a plot that many times have been shown. So I'm not going to go into the details, but just remind you that we expect to see very high signal to noise ratio of the massive black hole binary sources. And so the idea is that with this very high SNR, we should be able to test the no-Her theorem, right? It states that any black hole can be described by the mass and the spin. And into doing this kind of test, we are actually testing general relativity with quasi-normal modes. So this is the main goal, let's say, for my thesis. But let me start first with our ability to even detect or differentiate different modes, right? And modes from the complete waveform, so the inspired merger ring. So as you probably know, the waveform of compact object binary can be divided into 3 stages: the inspired, the merger, and the ring. Now, the inspired is when the 2 bodies start feeling the gravitational pulling to one another, so they start falling into one another. And these dynamics can be very well described by the post-Newtonian, where you include high orders of the velocity. Afterwards, we have the merger, where the 2 bodies combine, let's say, into one. And the only way to resolve these dynamics is by actually solving Einstein's equation, and that's where numerical relativity comes into play. And then finally, when we have the final black hole, it will relax into more stable state, and this is described by perturbation theory. So if we only assume this last stage, so the Riemann model, in perturbation theory, then we will have a perturbed black hole, and in the excitation of this black hole, it would emit gravitational waves that can be written or decomposed into quasi-normal modes. Now, the reason they are called quasi-normal modes is because of the boundary conditions that you have on the wave equation, and so your frequency will no longer be real, but it will acquire an imaginary part. So you will have a complex frequency that has the frequency and the damping time, right? And each of these frequency is actually labeled by the L and the M as the polar and azimuthal angular number. And here I'm just showing you an example of these quasi-normal modes in a source that could be in a source from the LISA band, let's say. And you can see the strain of all these modes and also the addition of all these modes, which is represented here in black, in the time domain. And so the idea is that we know all the values of this frequency, either the real part and the imaginary part. And actually they are cataloged, for example, by Berti and collaborators in this paper here. And what you can do is, once you know those values, you can actually make a connection with the mass and the spin. And a way of parameterize that is also given in the same paper of Berti and collaborators, and it's given in these 2 equations here. So a more visual representation of that, if you will, is given in a paper written by Gossan and collaborators, which is the plot I'm showing you here on the left side. You have the mass versus the spin, and with this kind of equation, you could see like all the values that you will get with the known frequency and damping time. And as you can see, when you have more than two modes, then you should be able to pin the mass and the spin, and that you do when you look at the lines. For example, here you will see that they all intersect at the real value, which is denoted here with this blue diamond, right? Now, if, for example, you were to have a deviation from these frequencies, then you will see what is on the right side, on the plot on the right side, where you have a deviation, where all the value of the mass and the spin will be shifted. So this is the main idea behind the testing of no-Her theorem. But as I said, we first want to know, or we want to test our capability of detecting these modes, let's say. So what we do is we try to compare different models with different quantity of modes in a Bayesian analysis, and for that we use the Lisa Beta software, which created by our chair here today, Sylvain Marsat, and collaborators. And it takes phenomenological waveforms, either from PhenMD, PhenMHM, or the effective one body with high modes, and reduce all the modeling, which just to make the waveform faster. And then it passes through the Lisa response. So you have to take into account, obviously, the orbits of the constellation, the delays between the different references frame, and also the GTI, which is the time delay interferometry for either first or second generation. And then as a sampler, I use Dynasty. I know a lot of people like to use better the PTMC, but in this case, we wanted to compare models by this bias factor, which is just the ratio of the evidence. And the good thing about Dynasty is that it gives you the evidence directly. So it's more easy to use, right? So our procedure is that we injected a source that we create with a PhenMHM. So we take into account 6 modes, which are the ones written here, which are the ones allowed by this software. And then we wanted to make the scenario the more real case scenario possible. So we use the second generation GDI. We also take into account the full response of Lisa. But then we also use a rescalization just to eliminate frequency-dependent perfectos that were common to the signal and to the noise. And as a source, we choose the Lisa Data Challenge Sangria catalog, a source that was in there that had a signal-to-noise ratio of 725, which by a recent talk that I heard from I don't remember the name right now, sorry. It was in the mean, so it's let's say a good source. And one thing I had to mention is that this kind of PhenMHM and PhenMD do not allow for precision, so it only allows you to have aligned spins, right? So these are the source of our parameter, and with those parameters, the source will look like this in this frequency domain, where you can see clearly the contribution of all the different modes listed here, and also the final addition of all of them, and also the noise, right? This noise is the science requirement, science requirement document noise. And once we have the signal, what we try to do is we let our code, our sampler search for different kind of models. So in the first model, we only have one mode, which is the 2-2, which is the most relevant one. Then the second model have 2 modes. Well, you can see that here we add the 3-3 and so on and so forth, up to 6 modes. So we let the sampler run, and finally we got our results. And here we decide only to show you like the most important parameters to test the Noether theorem, which are the intrinsic one, right? So we have here the parameters of the spin of the 2 masses, the chirp mass. Well, it's actually the logarithm of the chirp mass, and also the mass ratio, which in this convention is always bigger than 1. So the mass 1 is bigger than the mass 2. And what you can see is that the posterior distributions for the 3 different models. So with 1 mode, 3 modes, and 2 modes. And as you can see, the model with the 6 mode is almost perfect to the true value. And just to compare, I put the tables here with where we have the true value and the estimated value with the model with the 6 modes. And also, if you want to compare this by a bias factor that I've been telling you about, where it's only the ratio of the evidence, then you can see that the values is always negative, meaning that the analysis prefer the model of the 6 modes instead of all the other ones. And then we did the same thing, but let's say a more even realistic case where we inject also the noise in the signal. And then we also look for different modes. And here I wanted to show you only the 4, 6, and 6 modes, because here something kind of weird happened, and the model with 4 modes actually finds the true values better than the other ones. This is a preliminary result, so we are still trying to see why this is happening. But here I'll show you again in this table the true value versus the values estimated with a model of 4 modes. And yeah, once again, in the bias factor, you can see that at least up to the model 3, the model 6 is preferred. But if you want to compare with the 4th and 5th, this is still like something we need to see and take into account. And so with that, I'll go to my conclusions, is that we can do parameter inference with high accuracy when more modes are included, so we can actually distinguish them if they are present, of course. And this is just something that I wanted to remark, especially in comparison with ground-based interferometers, is that higher frequency and therefore higher modes become more relevant than in the other detectors. And just to finish, these are next steps and future considerations. I don't know if I'm running out of time or not, but I'm not going to go.
We have time.
Okay, otherwise I'm not going to go through all of them. Just let you know that this is just the tip of the iceberg, and we know there is still a lot of work to do, like the inclusion of the precision, maybe higher orders. Also, if we want to study only the ring down, then we have a problem of the choice of the truncation time, and then also maybe introduce some deviation. But if we do, how to do it in this inspired major ring down waveform, and how it would affect only the ring down or also the inspired merger part, right? And then, well, yeah, also we need to take into account, for example, for the overtones, so the mixing of the modes. So yeah, it's a very broad subject, and we are still digging into it. So yeah, that's all for me. So if you have any questions, I'll be happy to answer. Thank you.
Thank you very much. It was a very interesting talk. So we have time for questions. There's one from Jonas. Go ahead.
Yeah. Hey, Chantal, very nice talk. I had a question about the modes. So you were showing us nicely how you can include different modes and how that changes your predictions. I was kind of wondering about the reverse problem, if you like. So do you know for some likely future source, how many modes can we tell apart? What's the prediction there?
No, actually, that's something that we actually also want to do, right? Because for the moment, we only have 6 modes, so we're dealing only with 6 modes. But how many modes do we need to see, or we want to see? That will actually be determined by the SNR, I assume. So for the moment, we don't have higher modes, so there's not much I can tell you about it.
Okay, but so do you have any intuition at all? So 6 modes sounds quite optimistic for a detection in the future, I guess. But my intuition would be maybe 2, 3 or so as something we can really tell apart from the data. Does that line up with what you think as well?
I actually think that we need even higher modes. Okay. But this is just my my view, let's say, because actually of what I said, that because of Lisa transfer function, you expect that higher modes to be more relevant. So actually, if you compare with other signals, with other detectors, these 2 modes that are the 3.3 and the 4.4, they are less relevant. So maybe you don't have to see them. But in Lisa, the 5th mode, let's say, will be here. So you should be able to detect it too. At least when you have the L equal M, the M equal L, right? For the 5.5 or 6.6, let's say.
Right, understood. Great, thanks a lot.
Yeah, thank you, of course.
Thanks. I'm looking at other questions. Yeah, if I can just add a comment and what was just said, I concur. I think it depends which kind of source you look at, but supermassive black hole signals can be, if they're nearby, extremely loud, as now 1-2000, And I think the limit in what Chantal has shown here is just what was available in the waveform models that we had to work with. All right, if there are no other questions, I might have one myself. So just to understand, because you should actually, in the first example with your noise, you showed that if you try to analyze the signal without including all the harmonics that you have injected, you actually recover parameter biases, right?
Yes.
And this is interesting in some regard because it's often considered that these different harmonics, especially if they differ in the value of m, the azimuthal angle, are orthogonal in the sense that they have a dependency as e to the I m times the orbital phase. And as far as the inspire is concerned, say the 2-2 mode and the 3-3 mode, when you do the inner product between them, should be relatively small. They should be relatively orthogonal because they should have very different phasing. But this is interesting because it shows that I think it points towards the fact that the merger and the ring down is so important that the conventional knowledge that you would have from Inspire does not really apply, and you can actually have cross terms between these harmonics that are not zero. And if you ignore the harmonics, it's not simply that you lose some SNR, is that you can actually have biases. So it's very important.
Yeah, I think that too. And I think that especially here it's important when you add the model of 4 mode. So you actually adding this one here, the 2-1. It gives you also a lower frequency of the inspired power, which I think it's also important for the parameter estimation of the spin, which is you see that, for example, here these modes is not very good, but once you add it, it's a little bit better.
Okay. Thank you. So if there are no other questions here, Sirius will stop here, and
Okay.
we will reconvene. So thank you again for this talk, Chantal.
Yeah.
So we reconvene at 1/4 on the scheduled time to start with the talks of the second half of the session. So thank you all and see you then.
Thanks, Sylvain. Any of the speakers for the second session, second half of the session, who wish to test their slide sharing, please feel free to.
Hi, I'd be happy to try to share my screen, just to make sure everything's working. If I go full screen, can you see it?
Yep, that's perfect.
Okay, thank you.
Thank you.
I'll stop sharing.
Right. I'll just put up the mid-session coffee break slide for now. Hello, it's Mike here, IT support. If anybody would like to test their slides, any of the speakers would like to test their slides, you're welcome to do so. I can stop sharing. Just let me know. Okay, I see you're happy to try, Giovanni. I'll stop sharing the mid-session slide.
1 second. Is it all good?
That looks perfect. Yep, that's your slides. Great. So yeah, we'll start again in a few minutes' time. Okay. There. That's about 1/4 Sylvan. So if you would like to get started again, that would be great. Thank you.
All right. So welcome to the second part of this fun graphics and waveform session of the Lisa Symposium. We will be starting again. So if you want to share your screen, Lorena.
Yes, I'll do that.
All right. So the next speaker will be Lorena Magana-Zatuj from the University of Mississippi, talking about high precision read on fitting. So you have 15 minutes, and I will tell you a few minutes before the end, the time you have left. The floor is yours.
Okay, thank you very much. So my name is Lorena Magañez Artuche, and I will tell you about ring down fitting, and all of this that I will be telling you about is on recent work that I did in collaboration with Keith Mitman, Niv Kera, and Leo Stein, who is my advisor. So let me begin by asking the question, why are we interested in ring down? So we're interested in ring down because it provides us with nice calculations using perturbation theory that can help us understand the random properties of a binary black hole system. And because of that, it provides us with a nice way to test GR. It also gives us an independent test for when we're talking about like the in spiral, we can find the remnant parameters with the in spiral. We can estimate those. And with ring down, we can also get an estimate on what the remnant parameters are. And we can independently compare the two. And that gives us also a consistency check between perturbation theory and numerical relativity. We're also interested in studying this because there will be, third generation detectors, and of course, LISA, that will be sensitive to many more ring down frequencies. And because of that, we want to make sure that we are ready with very precise ring down models that we can take advantage of. So let me begin by just giving a quick overview on quasi-normal modes. So a ring down waveform can be described mathematically in such a way where it depends on this quasi-normal mode amplitude that depends on the mode LMN. It also depends on this decaying sinusoidal, which has this quasi-normal mode frequency. And then we have the last term, which is a function, a spin wave function, which is a spheroidal harmonic. Now, instead of working with spheroidal harmonics, we switch over to our spherical harmonic functions here. But the trade-off is that we then have to take into account this CLL'(M), which is our spherical spheroidal mixing coefficient, to go from one function to the other. And we do this for two reasons. The first reason is just because all the numerical relativity waveforms are already in spherical harmonics, so it's just easy to use it in that sense. The second reason is very important. So all of the frequencies that we're working with are actually complex. They're not purely imaginary or purely real. And so since they are complex, then the spheroidal functions do not necessarily form a complete basis, but the spherical harmonics do. So we switch this. So now how do we get each of these ingredients into our model? So we have to solve for Tucholsky's equation, which is a second order partial differential equation that luckily can be decomposed into the radial, angular, and temporal equations. So typically people use Lever's method, which is a continued fraction technique, to solve for both the radial and the angular sectors. But we instead just use it for the radial sector, and we employ something called a spectral eigenvalue method, which is actually outlined in Cook and Salutsky in my reference down here. And so the advantage of using that is that it's very fast, but also while we are solving for the quasi-normal mode frequencies, we're also able to solve for the spherical spheroidal mixing coefficients simultaneously. So it's kind of a 2-for-1 deal. And so by the time we solve this, we already have our quasi-normal mode frequencies, we have our spherical spheroidal mixing coefficients, and we already know what the spherical harmonics are. So the only thing that we are really missing at this point is our amplitudes, and that's what we do fits for. So just to kind of put everything together before moving on. So we have in ring down, we have to take into account retrograde modes. This is something that I will not speak too much about, but essentially each quasi-normal mode frequency has two solutions, a prograde and a retrograde, and usually people look at the prograde solution. The retrograde solution is only important in some systems. In others, it has a very small contribution, but either way, we take it into account. We also take into account the spherical spheroidal mixing coefficient, and we look at different overtones for our fits. And there are a lot of papers that I didn't get all of them on here, but I at least got quite a few of papers that have looked at all of these key ingredients, if not more than one combined. So what I will show here is two things. First, I will show how we fit multiple modes, how our algorithm works, and then I will tell you a little bit about how we fix the BMS frame. So these are the two main features of our paper. So just to show you how this works, so we take your favorite NR waveform and you rank the LM modes by power. So which one has the most power? Then you take the one with the most power, which is usually the 2-2 mode, 2-2-0 mode for many waveforms. And then we try to fit for the mode amplitudes by minimizing the residual power. So that is, we take this numerical relativity waveform and we subtract from it our model using the loudest mode. Once we minimize that, we take the amplitude that minimizes this equation and build an analytical waveform. Once we have our waveform, we can easily find the fraction of unmodeled power by this equation. And also very easily, we can just figure out what the mismatch is. However, if we are not happy with just modeling the 2-2 mode, we go back to this step and we take the second loudest mode, which could be a higher harmonic, or it could also be the next, the following overtone. It just depends. It really depends on the waveform. So we do this essentially, and it's what we call a greedy algorithm, to try to pick, instead of picking the modes manually, which we can do, we try to find a different approach for this. So that is the fitting algorithm of multiple modes over all times on the two-sphere. Now we move on to the frame fixing part. So I've mentioned that we work with waveforms, and you're probably thinking, okay, well, we work in this blue region, but that's actually not the waveform we look at. We instead look at waveforms that are more like this. So the difference between the two is just a different method to extract these waveforms. So on the left side, you have your typical extrapolated waveforms, which are the ones that have always essentially been used. But in SXS, we've started moving towards also making available the CCE waveforms. So Cauchy characteristic extraction waveforms. These waveforms are important because they include this memory effect. And this displacement memory is something that is not present in extrapolated waveforms, just from the construction of how one extracts the waveforms. But you will notice here that it seems that our ring down is now shifted upwards. So clearly there's something weird there. It's not going to 0 as we want it to go. And this is because it's super translated. The remnant black hole is super translated with respect to the PN post-Newtonian frame. And so what is this super translation? So this is from the BMS group, so the Bondi-Meissner-Sachs group, which is it's an infinite dimensional group for future null infinity when you have asymptotically flat spacetimes. So in math speak, it's a semi-direct product of the Lorentz group and super translation group. So essentially, we know that black hole remnants are in simulations are super translated with respect to the remnants that Tucholsky's equation was working in. So in Tucholsky's equation, you don't care about the past history of a black hole. You just have the black hole in its rest frame, essentially. And so when we have waveforms that look like this, that's clearly not in the rest frame because it's been super translated. So we have to do a BMS transformation from this super translated frame to what is called the black hole's super rest frame. And once it's in its super rest frame, we can do the ring down analysis. And this is kind of what the super translations do. So you're maybe wondering how that affects the strain. We've seen it visually, but how it can affect, how mathematically it can affect a ring down analysis. So if you do a super translation, you have this angle dependent time translation. U here is the Bondi time. So it's not just like a shift in space fully. There's also some mode mixing effect. And you can see it here. You have mode mixing of your strain plus this constant shift. So what does this mean for our analysis? So let me just show you how important it is to map to the correct frame. So here we have in blue, this is a numerical relativity waveform mode. This is a 2-0 mode. And if you're interested in the model, it's the 0305, which is a proxy for GW150914. So the 2-0 mode always, it's known to have the most memory, to display the most memory. And you can see here that at the end of the ring down, the waveform does not go to 0. And this is because it is super translated. This is just a regular CC waveform. And so when we try to fit it with our model, which is this orange dashed line, you notice that our model really struggles to actually to try to do something similar. And in the end, it just gives up and decays down to 0. Indeed, the residuals are also very high, so we are not really doing too much here. If instead we translate this to the superrest frame, we now have our numerical relativity waveform mode going to 0. And when we try to model it, our model has a much easier time. And indeed, the residual starts going 2 orders of magnitude and less improvement. And sorry, you want to look at the black line here. If you just do the constant, if you just do a shifting, then you get the red line, which is still pretty good, but it's not the right thing to do. So what happens when you combine this multi-mode algorithm and frame fixing? So we try to see the importance of doing using multiple modes. So here we have plotted the fraction of unmodeled power, but we've done it in the news domain. And the reason why we did this in the news domain is because power is naturally defined there. So it's just a more natural thing to look at. And on the x-axis, we have essentially the time at which our model begins. So in the previous talk, they've mentioned that we don't really know when ring down begins. So it's important that we look at all of these different times just to see what the behavior is like. So
just
if you just
tell you have 3 minutes left.
Okay, thank you. If you look at the solid lines, you will notice that with 5 modes, you still have a lot of the fraction of unmodeled power is still very high. But as you increase the number of modes you have to 20, 50, and 100, you start modeling or you start capturing more power in your waveform. So here are just some numbers. Just to tell you, so you can capture 98% of the power in your waveform with 5 modes, but you can do much more than that if you just start adding a larger number of modes. So okay, we can get the power of the waveform, but what does that mean for the mismatch? So we've done essentially the same plot, but we've done it with a mismatch. And now we're back to looking at the strain as well, no longer the news function. So it's not surprising that as you add more and more modes, the mismatch of your model decreases because you're capturing more power. Just for reference here, I added 2 lines that show, so this purple dash dotted line that shows if you just use a 2-2-0 and 2-2-0 modes, what this looks like, what your mismatch looks like. And I've also done the same for the overtone number. And these are all mode mismatches. So clearly you start tapering out. So it's really important to add more than just the overtones. It's important to add the overtones, but it's also important to add higher harmonics. And okay, so our mismatches look really low. Oh, I should mention, our mismatches start going very low, especially at times after like 15 M or so. But to make sure that we are not overfitting, we have this kind of grayish blue-black curve at the bottom. And this shows a numerical error. So by not going below this, we're okay with not worrying about overfitting. And now we want to recover some parameters. So if you just take the 2-2-0 mode, you notice that the error in your estimation, in your parameter recovery is quite high. And here we look at the masses and the spin magnitudes to calculate the error. And we do this for 86 simulations in this surrogate model and our hybrid 3D Q8. As you add more and more overtones, you will notice that, for example, the median in your error starts decreasing. But if instead you add 40 modes that include higher harmonics, not just the 2-2 mode, you can bring this down to a much lower order of magnitude. And it's kind of hard to push even lower, even if you are if you add more modes, you cannot really push too much lower on the errors. So this is already a very good improvement. And the last results I want to show. So this is just how important the super rest frame is when doing this multi-mode fitting. So on the horizontal axis, you have all different systems. Most of them are Q equals 1, but you have some Q equals 4 systems here with varying spins. And at the end, we have GW15 or 914 just for comparison. So let's ignore the bottom panel and just look at the top panel. If you look at the mismatch between numerical relativity and our model with 100 modes, you will notice that the mismatches for extrapolated waveforms are quite low, on the order of 10 to the -6, maybe 10 to the -5. And if you use CC waveforms, which are these waveforms that are super translated, you actually get really bad mismatches, but that's not very surprising because you're in the wrong frame. If then you do a BMS transformation to the super rest frame, you start getting these blue bars. And so you actually get much better mismatches than if you use extrapolated waveforms, which is not very surprising. So because they are more correct to use for a ring down. So let me just finish with a summary. So it is important to model multiple modes to be able to take advantage in future detections, especially because each system, depending on the parameters, may consider different modes more important. By being able to greedily make a model, one can get a 5 order of magnitude improvement over just picking maybe one mode or 2 modes by hand. Additionally, if we include waveforms that are in the super rest frame, CC waveforms that are in the super rest frame, we can also get a 5 order of magnitude improvement there on the mismatches. And so we will be packaging all of our code and make it publicly available. So if people want to build their own models, whether they want to pick their own modes or pick a specific number of modes, they can do that. But we haven't begun doing that. We've just started talking about it. So it will be a while. And we're also currently working on building a ring down surrogate model that hopefully will be useful for LISA and for other detectors. And that is all. Thank you. I'd be happy to take any questions.
Thank you very much for this very interesting talk. We're a little bit over time, but we have time for at least one question. I don't see one so far. I would have one myself. So you have a greedy algorithm looking for different modes and potentially various sets of overtones. How continuous is the result when you change parameters? If you move from a waveform to a neighboring waveform, do you extract the same set of modes and overtones, or do you end up with a different set of modes and overtones?
Yeah, so that's a good question. We haven't looked at it in detail, but we have looked at a few of waveforms. So more or less, the top maybe for vanilla waveforms, you get very similar modes being the most important, especially like the top 3, the top 5 modes more or less are about the same. However, when you start having systems that have precession or are like anti-aligned, you will have different modes. For example, if you have a system that's very high in mass ratio and has a high negative spin, you're gonna get the retrograde modes to be more important than the prograde modes. But it really depends on the mass ratio but for most, I think the 2-2 mode is always there. And then it just depends. The 2-0 mode, for example, that exhibits memory is more important in some cases than others, but we have not done a thorough study on that yet. We're working on it.
Thank you very much.
Thank you.
So I'm looking, but it doesn't appear that we have other questions. All right, so let's thank Lorena again for this very nice talk. And we're going to move to the next speaker, who is Massimo Vaglio. Do you want to share your slides?
Yes, sure. Okay.
All right, so the next speaker is Massimo Vaglio from Università di Roma La Sapienza, and he's going to talk about supermassive boson stars as its targets concerning multiple moments and scalar interactions. So you have 15 minutes. I will tell you a few minutes before the end. The floor is yours.
So, hi everyone, I'm Massimo Vaglio from Sapienza University of Rome, and first of all, I would like to thank you, the organizers, for the opportunity of giving these talks, and also everyone who is connected and interested to this topic. So I will talk about supermassive boson stars as LISA targets and about the possibility of constraining multiple moments and scalar interactions with future observations. So the motivation for this work comes from the fact that gravitational waves allow to probe the nature of compact objects with the unprecedented accuracy, and this in turn gives us the opportunity to test some theoretical models which have been proposed to represent compact alternatives to black holes, so to challenge the black hole paradigm, and that have been developed in different theoretical frameworks, but each of them implying the presence of some new physics yet to be discovered that would come into play, and which is an intriguing possibility. One of the way in which the gravitational waves carry information about the nature, about the inner structure of compact objects, is through their multiple moments, the multiple moments of the compact objects, which affect their dynamics when they are in binary systems, and in turn the gravitational wave emission. So, for example, if we are dealing with stationary and asymmetric objects, then the surrounding space-time will be characterized by two sets of scalar quantities, which are the mass and current moments, which, for example, for a Kerr black hole, satisfy this simple relation here, where chi is the adimensional spin and m is just the mass of the object. But this will be in general not true for a generic compact object, since deviation from the black hole value can be a signature of a detection of one of these objects with gravitational waves. So I will focus on a particular class of compact objects, which are boson stars, which can be defined as solutions of the Einstein gravity minimally coupled to a complex scalar field described by this Lagrangian. The equation describing their equilibrium configurations, which in general require numerical methods to be solved, are just the Einstein equations plus this Klein-Gordon-like equation, in which V is the potential term, which contains the mass term of the field as well as self-interactions. And here, self-interactions for the stars plays an analogous role to what the equation state does for neutron stars, in the sense that different self-interactions give rise to different families of boson stars with different characteristics. For example, the way in which the maximum mass allowed for the model scales with the mass of the boson, and eventually with the coupling constants of the theory. To have stationary and axisymmetric configurations of the space-time, one has to assume these ansatz for the scalar field, where this n of r is called the azimuthal winding number, and it has to be an integer, and omega is just the angular frequency of the field. So the case that we studied is the one in which the self-interactions take the form of a quartic self-coupling term. And we also studied the large self-coupling limit. And this is because this is the region of the parameter space where this configuration are expected to be stable, and also which allow for the most compact and massive configurations. And in this approximation, the coupling constant of the theory can be completely factored out from the numerical calculation to appropriate rescalings. And one can also apply a convenient method to solve the equation, which have been applied to this class of boson star in this reference here, which is a self-consistent field method, which basically means that after having introduced a suitable line elements, like the Lewis-Papapetro coordinate, which are expressed in which the metric is expressed in terms of these four unknown functions, then one can turn the Einstein equations into an integral form, which allow basically for an iterative scheme of resolution, one in which one starts from an initial guess for these functions, and after a few iterations, the solution converges to the desired solution characterized by some parameters given in input. And then the mass and current moments can be read off the asymptotic expansion of the function, of the metric function. So let's see how the Bose-Star mass scales. So as I was saying, in this large self-coupling limit, the coupling constant can be removed by rescaling to dimensionless quantities. And they simply set the overall scale of the problem through this effective combination, which we call MB, which has the dimension of a mass. So basically, from the dimensionless quantities, one can restore physical units by multiplying each dimensionless quantity by a given a given power of MB to match the correct dimension in mass of the quantities. For example, the mass of the boson is the mass of the boson star is simply given in units of the effective coupling MB, and for you can see, for example, that for this model, the maximum allowed value for non-spinning boson stars is around 0.06 MB, and this limit can be exceeded a bit considering spinning configuration. And if you want to explore the possibility of constraining boson star with future observations, so we want the range of masses to be in the range of current and future detectors, we can estimate what this range is by considering a value around the maximum mass for the spherically symmetric configurations, and then restoring physical units. Basically, one can see that the whole range of the whole spectrum of physical black holes can be reached easily by varying the values of lambda and the values of the mass of the bosons, and without even recurring to ultralight scalar fields in this model. So these are our results for the multiple moments of these rotating boson stars induced by the spin. And in this plot, you can see the quadruple and the octuple moment. Actually, the reduced version of the quadruple and octuple moments, the moments divided by powers of chi and m in order to have the corresponding quantities for a black hole to be both equal 1. For example, if you look at the plot on the left, you can see this reduced quadruple moment as a function of the spin for different values of the boson star mass given in terms of the effective coupling MB. And basically, you see that the smaller is the mass of the boson star, which also means the smaller is the compactness, the larger is the value of the quadruple moment, and at the maximum value and at the minimum value of the quadruple moment, corresponding to the most compact configuration, is well disconnected by the value the value of 1, which is the corresponding value for a black hole. You can find the data and more about this in this work, this paper here, done with collaborators in Sapienza, Costantino Pacilio, Andrea Maselli, and Paolo Pani, and also a discussion of this result in comparison with previous works, from which we found slightly small deviations, as I will say again in the very end of the talk. A thing that I would like to mention is that we also found that the reduced quadruple and octuple moment are simply connected to the tidal deformability of these objects, and in particular, if you take the reduced quadruple and octuple moment as a function of tidal deformability in a log scale, this relation appears to be linear, and also the relation between the quadruple and octuple themselves, which could be a hint of a universal relation, which could hold for boson stars as they are known to hold for neutron stars as well. So what we did with this data that we provided for the multiple moments is to build a coherent waveform model, which consistently includes the different contributions from the multiple moments and the tidal deformability to measure, to investigate the ability of future detector to constrain multiple moments and the scalar interactions. So the expression for the quadruple moment can be given in terms of the reduced quadruple, which can be obtained as a function of the spin and of the mass of the object by interpolating basically the data that I showed in the plot before. And the tidal deformability for these objects can be obtained in terms of their mass and the effective coupling, exploiting this relation, which is given in this paper, where this is the definition of the tidal deformability, which measures the response of the object to the tidal field of the companion. And in this way, exploiting these two relations, we have that both tidal deformability and the quadruples are function only on the mass, the spin, and the effective coupling of the theory. So they are coherently included in the model. And then we built we focused on the spiral stage of the merger of a binary boson star, and we modeled the waveform using a post-Newtonian expansion in the frequency domain. And we basically truncated the amplitude at 0 pn order, while in the phase which contained most physics of the problem, we retained point particle terms up to 3.5 pn and adding quadruple corrections and tidal corrections coherently included in the way that I showed before as function just of the masses, the spin, and the effective coupling of the theory. So then the idea was to study the ability of LISA and in general of future detectors to measure directly the effective coupling of the underlying scalar theory through observation of boson star binaries. So directly doing parameter estimation and measure and investigate the precision of a measure of MB. And we used for this a Fisher matrix approach in this paper here, which holds in the limit of large SNR. And we basically, so that in this limit, one has this expression for the posterior as centered on the true values of the parameter, and then the uncertainty is simply given by the diagonal elements of the inverse of the Fisher matrix. And what we obtained
about 3 minutes left.
Okay, thank you. And basically, we consider the following scenario in which we have two individual masses, which are so with which are similar and are both close to the most compact configurations. We consider this mass scale for this range of values of MB, which reflects in this range of values of the masses of the binaries, and 3 different configurations of the spin. Then what we found is that in this way, the error on the effective coupling MB are even at the sub-percent level in the most optimistic configurations, which of course are the one in which the spin are larger, because these are the configuration in which also the quadruples enter and play a role, which is a really nice result that I have to point out that we did with in this work here, which was before we had this new data for the quadruple, for the quadruples and the octuple moments. So what we are doing now is to devise a full Bayesian analysis, of which here I show just this is just this plot is just for illustrative purpose, but the idea is that to do injecting and recovery of boson star binary signal with PLP, which is an inference library, to assess also the ability of current detectors to measure the effective coupling, since here with lower SNR the given the lower SNR, the analysis with the Fisher matrix will not work. And we hope that we will have soon results, more results on these, even to confirm the results that we obtained in the matrix, which is just, in any case, an explorative tool. So to conclude, we provided accurate data for the multiple moments of rotating boson stars with the quartic self-interactions in the strong coupling limit. We developed a waveform model for the spiral stage, which consistently includes tidal and quadrupole effects. The quadrupole and octuple moments that for which we provided data with our numerical methods agree with previous results for high spin, as I was saying before, but in the low spin region, we found that the absolute values are larger by a factor of respectively 2 and 3, which also means that this will increase our ability to disentangle boson stars from black holes using multiple moments. We uncovered simple relations linking the multiple moments and tidal deformability, also known as the love-Q relation. And we show that LISA will be able to infer strong constraints on fundamental coupling constants of the underlying scalar theory from observation of both star binaries. So feature perspective and extension of this work include repeating the analysis in a full Bayesian setting, as I was saying, and including these new more accurate data that we have, and considering different self-interaction, of course, in first place to study the universality degree of this relation covered, because of course we found simple relation just for one realization of the self-interactions, and with different boson star models and with different studying the impact on the multipolar structure, we can also study the possibility to distinguish signal from different Bialtz models and so basically perform model selection. And so thank you for the attention.
Thank you very much, Massimo, for this very interesting talk. We have.
Sorry, I interrupted the screen sharing, but I can do it again if there are questions that need the slide support.
Okay, yes. Trying to see if there are questions in the chat or hands up. I didn't see any. Right, so I had a question, but this is not, this is maybe a bit too open. Is yeah, that you find the universality relations and this reminiscent of these high love Q and so on relations that were found and got a lot of attention for, notably neutron stars. Do you want to comment on that? Or
yes. The thing is that even if one could expect some relation about the tidal deformability and the quadrupole moment in any case, it's by no means obvious that the relation should be so simple as the one that we uncover, which is basically that they are the relation is linear on a log scale. And I didn't mention this, but this holds in the low spin region, as it's true also for neutron stars. And so I would say that the fact that this relation is so simple can be an encouraging sign that this relation will also for different potentials. But I mean, there are no theoretical motivation for these, and I would say that also for neutron star, it's not so obvious why they hold. And in that case, they could be related with the fact that the equation of state on the beside the inner core, the equation of states are similar. In that case, this maybe this could be completely different for boson stars. So.
Okay, I see. It's intriguing. Thanks. We also have a question from Sayantani. Please go ahead.
Hello. Yeah, thanks for the talk. I just had one question, which is from the slide where you showed the Bayesian analysis. So, and I noticed that it's for non-spinning case. So, and I guess you did using the scaling relations you got for the non-spinning case. I'm not sure, but I'm just wondering, is it easy to extend this analysis for a spinning case as well?
I'm not sure that I understood completely the question because I cannot hear you very well. Are you asking about the tidal deformability relation?
Can you hear me well now?
Yeah, maybe it's better now.
To simplify my question, I'm just wondering for the Bayesian analysis case, is it easy to extend for spinning cases as well? Because I noticed that you have kept the spins at 0. So yeah, just a clarification.
No, okay. No, as I said, you're referring to the corner plot in the last slide, right?
Correct. Yes.
Yeah, no, that was just for an illustrative purpose. So this is an ongoing work, but yeah, we are still working on that. I mean, the corner plot comes from a real injection and recovery, but yes, it's just with the tidal, so does not prove yet my point. The fact is that we are handling carefully the correlation which arises among different quantities, and so we still don't have results on that for the fully for the Bayesian analysis. So that plot was just to show the proof of concept, let's say.
Okay, thanks.
Okay. Thank you very much. We can thank the speaker again for this nice talk. And we're going to move on to the next speaker. So, Pankaj, if you want to share your screen.
Yeah.
All right. So the next talk is going to be by Pankaj Saini on project and multiband constraints on dipolar gravitational radiation from eccentric binary black holes. So you have 15 minutes, and I will give you an indication 3 minutes before the end. The floor is yours.
Yeah, thanks. Yeah, so my name is Pankaj. I'm a PhD student at Chennai Mathematical Institute, and I'm working with Professor K.G. Arun. So first of all, I would like to thank the organizers for giving me the opportunity to present this work. And I'll be talking about the projected multiband constraint on dipolar gravitational radiation from eccentric binary black holes. So we know, as you know, in GR, that the lowest order gravitational radiation is quadrupolar in nature. The emission of dipolar and the monopolar emission is forbidden due to the conservation of matter stress energy tensor. And the luminosity of these gravitational waves in GR goes as v to the power 10, where v is the velocity of the two compact objects in a binary system. And if the space-time around these black holes or the compact objects is modified due to the excitation of the scalar fields, this may induce the scalar charges on these black holes. And when these black holes move around each other, this may produce scalar waves. And these scalar waves carries away additional energy from the system, and whose luminosity goes as this equation, which is proportional to the difference in the scalar charges of the two bodies and velocity to the power 8. So this difference of the powers of 2 comes due to the fact that this radiation is dipolar in nature. And these changes will appear as a correction in the gravitational phase, as can be seen from this equation. The gravitational phase is proportional to the difference in the scalar charges of the two bodies and v to the power minus 2. So in the post-Newtonian counting, this v to the power minus 2 term is known as the negative 1pn term, which dominates at low velocities or low frequencies. And these changes can also be seen from this plot. So this plot shows the gravitational waveforms in GR and in modified gravity. So due to the additional loss of energy from the system, the merger of these black holes will happen at an earlier time than in GR. So currently, the gravitational wave detectors observe these compact binaries very close to the merger when the binaries are moving very fast. And if there is any dipole radiation, it will be suppressed at this stage. And as I said, the dipolar radiation is a low frequency effect, and LISA will be observing in the low frequency spectrum. And when the binaries are far apart and moving slowly, so the LISA will be very effective in detecting the presence of dipolar radiation. And furthermore, if we can combine the low frequency observation with the high frequency observations of the ground-based detectors such as Cosmic Explorer and the Einstein telescope, this may further lead to an improvement in the dipole bound. So currently, LIGO Virgo uses the quasi-circular waveform for the parameter estimation and testing GR. But it is also very likely that when these binaries are spiraling in the LISA band, they still possess some residual eccentricity. So, so the eccentricity is a sharply decreasing function of gravitational frequency. As I said, the emission of gravitational wave carries away the energy and angular momentum from the system, and the emission of binding energy tends to decrease the orbit of the binary, and the emission of angular momentum tends to circularize the orbit of the binary. And the circularization happens very fast, as can be seen from this plot. So if you start with a very high eccentric binary around 0.9, which is emitting at 10 to the power minus 2 hertz in the LISA band, and by the time this binary enters the frequency band of the ground-based detectors, the binary becomes almost circular. But there are some formation channels, such as the dynamical formation of compact binaries in dense environments, such as globular clusters and the nuclear star clusters, which can produce highly eccentric binaries. And when these highly eccentric binaries enter the ground-based detectors, they still possess some residual eccentricity. And there have been numerous work on this topic. So if we use the quasi-circular waveform for the parameter estimation of these eccentric sources, this will introduce a systematic bias in the estimated parameters. And these systematic biases will mimic the deviations from GR. So in this work, we will quantify the effect of eccentricity on the dipole bound and see how these dipole bounds are changing when we use the eccentric waveform instead of circular waveforms. So to give an overview of the systematic biases, so these biases are the difference between the best fit value of the parameter, which maximizes the likelihood to the data, and the true value of the parameter. So if we consider an approximate waveform, which is given by the approximate amplitude and the approximate phase, so in our case, this approximate waveform is the circular waveform, and then there are eccentric corrections to the amplitude and the phase, delta A eccentric and delta psi eccentric. So, and using the Cutler and Wallis-Murray formalism, we can calculate the systematic biases on these parameters. So, which is given by equation 4, and the sigma AB is the covariance matrix, which is calculated using the approximate waveform. So, in our analysis, we neglect the eccentric corrections to the amplitude, but consider only the eccentric corrections to the phase. So, and we use a Taylor F2 eccentric waveform model. So this waveform model can be decomposed into the circular and the eccentric part of the waveform. This circular part is the standard circular 3.5 pn phase. And the structure of this eccentric phase can be seen from this expression. So this is an expansion in powers of V and V naught. And this phasing incorporates the leading order effect of eccentricity, which is E naught square, and this V naught is defined as pi m f naught, where f naught is the reference frequency at which we define our initial eccentricity E naught, and this waveform is valid in the small eccentricity limit less than 0.2. So all these waveforms are in GR, as I said. So we want to correct these waveforms for the dipole correction. So for that, what we do, we parameterize the gravitational flux as equation 7. So this is the gravitational wave flux, and this is the leading order GR flux, and this B is called the dipole flux parameter, which quantifies the strength of the dipole emission. And these corrections to the phase will be propagated to the gravitational phase, which is shown in equation 8 and 9 for the circular and the eccentric part. So in the circular part, these corrections appear like this, and in the eccentric part, these corrections appear like this. So using this, we calculate the bounds on this dipole parameter. And we use the Fisher information matrix to get the bounds on these parameters, which gives the 1 sigma width of the distribution around these parameters. And our parameters of the waveforms are the Tc, phi c, the time and phase of coalescence, and m is the total mass, and eta is the symmetric mass ratio. The chi1, chi2 are the two-dimensionless spins of the binary, and b is the dipole flux parameter. And now we calculate the statistical and systematic errors in the laser band due to the neglect of eccentricity, and see at what eccentricity these systematic biases become significant over the statistical errors. And we fix the observation time for laser 4 years. So in this plot, we show the systematic and the statistical errors. Systematic errors are shown by the slanted line, and the statistical errors by the horizontal line. And this is E naught. E naught is the eccentricity, initial eccentricity, which we defined at 10 to the power minus 2 hertz. And this is for 1509-14 like systems, because for 4 years of observations, these systems enter the frequency band of LISA at this frequency. So as the eccentricity of the source increases, the systematic biases increases and becomes comparable to the statistical errors at an eccentricity of 2 into 10 to the power minus 3, and becomes an order of magnitude larger at 10 to the power minus 2. So if you see that if a source with an eccentricity of around 10 to the power minus 3 is observed in the laser band, the systematic biases will be more than the statistical errors, and it will contaminate the bounds on these dipole parameters, and it may lead us to claim a false deviation from GR. So this is our motivation. Now if we use the eccentric waveform and see like what are the effect of this eccentric waveform on this dipole bounds. So for that, so in Barose et al. Have studied the multiband bound on the dipole term using the circular binaries. So now we extend their work by using the eccentric waveform. So for that, we consider 300 binary black holes distributed uniformly in a foam-moving volume up to a luminosity distance of 1 gigaparsec, because LISA may not be able to see these stellar mass binary black holes beyond redshift 0.2. And the masses of these binary black holes are drawn from GWTC3 like population, which follow the power law plus peak model. And the spins are assumed to be aligned or anti-aligned with respect to the angular momentum of the binary. And the magnitude of the spins are drawn from the default spin model. And the eccentricity of these binary black holes is assumed to follow uniform distributions, which are defined at 10 to the power minus 2 hertz. So most of these stellar mass binary black holes will be quiet in the laser band. So here quiet I mean will be indistinguishable from the noise in the laser band. So it depends on what are the SNRs of these sources in the laser band. So in an idealized template bank requires an SNR of 14 to 15 in the laser band, but which can further be lowered to 9 with the help of ground-based detectors, because ground-based detectors measure the source parameters pretty well. And this SNR can further be reduced to 4 to 5 with the help of ground-based detectors. So in our case, we choose a LISA SNR threshold to be 4. And with this SNR threshold, only 5% of our binary black hole population crosses this SNR criteria. And using this 5% of the sources, we calculate the 1 sigma combined bound on the dipole term. So this plot shows the bounds on the dipole flux parameter in the different detectors. So if you see in the Cosmic Explorer band, the bounds are of the order of 10 to the power minus 5. And in the Einstein telescope does little better. The bounds are of the 10 to the power minus 6 because of the better low frequency sensitivity of the Einstein telescope. And as expected, the LISA does a much better job. The bounds are of the order of 10 to the power minus 9, which are 3 orders of magnitude better compared to the ground-based detectors. This is because at low frequencies, the dipole radiation is abundant, and the dipole radiation is dominated at low frequencies. So LISA can measure these bounds very precisely. And further, if we can combine the low frequency observations of LISA with the high frequency observations of the ground-based detectors, the bounds further improves by an order of magnitude. They become from 10 to...
You have 3 minutes left about.
Okay, thanks. So if we combine the bound from the space-based detectors and the ground-based detectors, the bounds further further improves by an order of magnitude. And this is because of the breaking degeneracies between the various parameters in the waveform. So when we had the two Fisher matrices from the two detectors, the several off-diagonal terms cancels away and it gives a better estimation of the parameters. And similarly, if we combine the LISA with the Einstein telescope observations, it gives a similar kind of bound, and adding a further detector does not improve the bound much. So now if we use an eccentric waveform over these eccentric sources, the bounds becomes little weaker in all the detectors, and this is expected because now you are adding an extra parameter to the waveform, and so the information available in the signal is distributed among the different parameters, and because of various correlation of eccentricity with the other parameters, the bounds becomes little weaker. And if you want to combine these, if you want to compare these bounds with the currently best measured bounds of GW17 or 17, these bounds lie here, which are of the order of 10 to the power minus 5. And so if you see that the combined multiband bounds are 4 orders of magnitude better than the currently best measured gravitational wave bounds. And further, if you want to compare with the pulsar bounds, these bounds lie here. So the circular one does a little better job, but the eccentric ones are a little weaker compared to the pulsar bounds. And pulsars are very effective in constraining the dipole term. This is because of the longer observation of these sources. And because in this case, it was the 16 years of observation. So, but how these bounds will map to the actual bounds will depend on the properties of these sources and the particular theory considered. So to conclude that a subpopulation of binary black holes may have non-negligible eccentricity when they are observed in the ground-based detectors, and using the quasi-circular waveform for the eccentric sources will introduce systematic biases in the estimated parameters, and this may mimic the deviations from GR if the systematic errors become greater than the statistical errors. And we found that in the LISA band, the systematic biases on the dipole term becomes greater than the statistical errors at an eccentricity of 10 to the power minus 3 and 10 to the power minus 2 Hertz. So considering a more realistic eccentric binary black hole population modifies this dipole bound to 4 to 7 times, becomes worse than the circular counterparts. So thank you very much. Now I can take questions.
Thank you very much for the very interesting talk. So we have time for questions now. Okay, I don't see any question for now. So maybe I can ask one myself. So when you talk about the combined bounds that you get from LISA plus 3G detectors, I understand that you have done it with all the parameters, but did you look at what are the parameters that bring you most information? What I'm thinking of is there is an approximate way of representing the, say, multiband observations, which will be essentially take these observations and then say that the ground-based tells you the time of measure, primarily, because that's what it measures very well, and that LISA does not measure very well. Do you have a sense of how good that approximation would be?
Sorry, I could not follow the question properly. You're breaking for me a little bit. Can you say that again, please?
Yes, sorry. I was wondering because when you combine information from the LISA band and the 3G band, there is one distinctive information that the thing the measure brings you is really the time of measure. And
sorry, time of what is it?
Time of coalescence, time of measure.
Okay. Yes, yeah.
So I would expect that this is the dominant information that helps you reducing the bounds. I understand that you did more than this. I was just curious whether you checked that this is indeed the main information that you take.
Yeah, so time of coalescence is one of the reasons which improve these bounds, but then these other parameters such as so the chirp mass can also be measured well in the LISA band, but there are some other parameters like So I'm not sure particularly like which parameter contributes more to the improvement of the bounds, but as you said, the time of coalescence can be one of them. But I think it's not just the time of coalescence, but it's a combination of all the parameters, I think, which improves the bounds when we combine the two Fisher matrices. So for that, you need to check like which of the off-diagonal terms cancels in corresponding to that entry of the element.
I see. Thank you. Okay, let me see. I don't think we have other questions. So let's thank the speaker again for this very nice talk. And we can move on to the next speaker now. So Giovanni, if you want to share your screen.
Yes.
All right. So in this next talk, Giovanni Maria Tomaselli will, from University of Amsterdam, is going to talk about ionization of gravitational atoms. So you have 15 minutes. I will tell you a few minutes before the end, and the floor is yours.
Okay, thanks a lot. I'm Giovanni Maria Tomaselli, PhD student at the University of Amsterdam. Thanks for giving me the opportunity to talk. Here I will talk about gravitational atoms in binary systems. So, okay. So this talk is based on work done with Professors Daniel Baumann and Gianfranco Bertone at the University of Amsterdam, together with John Stout from Harvard. And there are actually two versions of this work, a long and detailed version and a short version, which focuses more on the gravitational wave observables. And it's more readable and is free of many technical details. And also I have to say that this work builds on previous papers by other people in Amsterdam who have studied similar topics. Okay, so fundamental physics with gravitational waves. So if you ask a particle physicist how to discover new particles, they would likely say, go to higher energy. And in fact, this is how historically most particles have been discovered. However, it is possible that new physics actually hides at weaker coupling rather than higher energy. And in this sense, as we will see, black holes and gravitational waves can be a probe of new physics. For example, of fields who may couple only gravitationally to the standard model. What kind of new physics are we considering here? Ultralight bosons will mainly focus on scalars. And by ultralight, I mean with mass less than about 10 to the minus 10 electron volts. Now, the motivation for these particles is mainly twofold. There are several theoretical models of beyond standard model physics who predict such axions or axion-like particles, but there are also phenomenological models such as models of dark matter who employ this kind of ultralight hypothetical particle. Why are these ultralight bosons interesting when talking about black holes? It's because of the superradiance instability. So basically, this is the wave analog of the Penrose process. If you take a Kerr black hole, and if in nature there is such an ultralight boson field, the Kerr black hole is actually unstable in that scalar modes around the black hole will grow exponentially with time. Their occupation number will grow exponentially. Now, the most interesting thing about superradiance is that it only needs two ingredients, a spinning black hole and a boson with about the right mass. You don't need any background density, any other assumption. If you have these two ingredients, you get superradiance. What is the right mass? Well, you only construct one-dimensionless parameter, this alpha. It's called the gravitational fine structure constant, which is basically the ratio of the gravitational radius of the black hole to the Compton wavelength of the field. And for about solar mass black holes, then the mass of the scalar mu has to be around 10 to the minus 10 electron volts. If you take more massive black holes, then mu has to be correspondingly lighter. The mass in the cloud can be actually up to 10% of the mass of the black hole. That is quite a lot of mass. And another interesting and maybe surprising thing about superradiance is that the final state of the system resembles the hydrogen atom. This is actually, this should actually be that surprising in that the gravitational potential at large distances scales as 1/r, just like the Coulomb potential. And therefore you get hydrogenic wave functions labeled by the same quantum numbers you find in atomic physics. That is 1, n for the energy, and then 2, L and M for the angular momentum. Only some of these states will be unstable and will grow due to superradiance. The fastest one is generally 2 on 1. Okay, so our goal is to study what happens when such a system, such a black hole plus cloud called gravitational atom, because of this analogy, is placed in a binary system. So we mostly have in mind intermediate to extreme mass ratios spirals, where we can talk about a big black hole with a cloud and a small object that orbits around it and eventually spirals in the cloud. So the orbiting companion will perturb the cloud with its gravitational potential at increasing frequency. There has been some work, some previous work by people in Amsterdam mainly, but also other people, that found orbital resonances, in that at specific orbital frequencies that match the energy difference between different states of the cloud, transitions between different states of the cloud can be triggered. So the cloud can go to a state with lower energy to one with higher energy, or vice versa. And the back reaction of this process on the orbit can create so-called floating orbits or sinking orbits, depending on whether the orbit is spiraling quicker or slower than expected in vacuum. In a generically later stage of the spiral, when the companion goes actually through the cloud, it is expected that there must be some sort of dynamical friction because it's going through such a dense medium. And this will in general change the dynamics of the system and therefore the ensuing gravitational waveform. So how do we compute self-consistently this effect? And this is the main topic of this work. Well, the spectrum I was showing before is actually not complete. To have a complete spectrum, you have to add these towers of unbound states, which have energy greater than 0, and correspond to free particles, which feel the gravitational attraction of the black hole, but nonetheless free to escape to infinity. When the orbital frequency is low enough, lower than the separation between the energy separation between the bound state and the continuum, then transitions between the bound state and the continuum cannot happen because the fundamental quantum of energy that is given by the companion is not high enough. But when the companion goes over this threshold frequency, then it can excite these transitions between the bound state and the continuum in analogy to what we call the photoionization in atomic physics, or photoelectric effect, if you want. In that case as well, it's very well known that there is a certain threshold energy above which the effect can actually happen. So how do we compute this? If you want to do this properly, taking into account the in spiral of the companion, it's actually pretty technically involved, but the main result is correctly captured by Fermi's golden rule applied as if the companion was not in spiraling. This means that schematically, the transition rate between the bound state and the continuum, this gamma, is proportional to the so-called level mixing, that is the matrix element of the perturbation between the initial and the final state. And this delta function is taking care of selecting the states in the continuum with the correct amount of energy. You can sum that up, you can sum that rate up all over all unbound states to get the total, what we call ionization power. So the total amount of energy per unit time that the binary pumps into the cloud. Now we can evaluate this numerically to find this plot. So a few comments are in order about this plot. So on the x-axis, I'm showing the orbital separation under the assumption of quasi-circular orbits in units of the half Schwarzschild radius. On the y-axis, I'm showing the ionization power normalized by the power emitted in gravitational waves. So you may notice that the scale of y-axis is large. This means that this ionization process can actually extract from the binary more energy than gravitational waves, even by orders of magnitude. And this is what I'm showing this plot is even a conservative estimate in some sense. Second, you may notice that the ionization power has these jumps, these discontinuities. So what's going on? Well, I told you before that there is a threshold activation frequency for ionization to happen. Well, actually, the gravitational perturbation is not monochromatic. So you can decompose it in Fourier components, and each monochromatic component will contribute, say, independently and have a different activation frequency. And at all these activation frequencies, you will get these discontinuities. Now, if you do things properly and take into account the radial motion of the companion, that is the non-zero rate of spiral, you find that these, of course, are not actual discontinuities. They are smoothened out by oscillations, but with realistic parameters, these oscillations are very short. So these are effectively discontinuous features. Now, before exploring how this ionization changes the evolution of the system, I want to say that we also include another effect, which is the accretion of the cloud onto the companion in case it is a black hole. This effect, if you want, it's somewhat less interesting than ionization in that it doesn't have these discontinuity or stuff like that. However, it is important because the companion, the black hole in this case, is going through such a dense medium. So if you didn't take into account ionization, you would find actually the fractional increase of mass would be even of order 1. This is somewhat decreased by the inclusion of ionization, but it's still an order 0.1 effect. So we have to take that into account. Okay, so to see the—
Giovanni, you have about 3 minutes.
Thanks. So to see the effect of ionization and accretion on the dynamics, we solve a very simple case just in the Newtonian approximation for quasi-circular orbits. I know this is a toy model, but it does show the main effects and observables of the effect. So we solve for 3 variables, which are the orbital separation of frequency, the mass of the companion, and the mass of the cloud. So the first plot I want to show is the evolution of this separation as function of time for an intermediate mass ratio in spiral. So the black line is what you would have if there was no cloud. The blue and the orange thick lines are the full solution of the system, including both ionization and accretion, in case the binary is co-rotating or counter-rotating with the cloud. As you can see, the spiral is shortened by even hundreds of years in this case. And in general, as soon as the ionization power overcomes the power emitted in gravitational waves, there is sort of a plunge here and here, and the merger happens much quicker. But perhaps the most interesting feature that is imprinted in the gravitational waveform is seen plotting the orbital frequency, which here is rescaled in such a way that to lowest order, the vacuum case looks like a straight line. So you see that the frequency has these kinks at some specific orbital frequency or orbital separations. These are, of course, the direct consequence of the quasi-discontinuous features in the ionization power. So a discontinuity in the ionization power translates into a discontinuity of the first derivative of the frequency. Now, the position and in some sense the amplitude of these kinks in the frequency evolution are directly linked to fundamental physics, like the mass of the boson in terms of the fine structure parameter alpha introduced before, and the state of the cloud here, which enters by the principal quantum number n. And it happens that for an intermediate mass ratio in spiral, these kinks fall in the Lisa band, are about in the millihertz range. So in conclusion, when you have such a system, such a gravitational atom in a binary, the spiral dynamics is changed so much that it's not just perturbed by the presence of the cloud, but it's driven by it. And if we use vacuum waveforms to find such systems, we may fail. There are undergoing studies about that because the evolution is so different. It's not just a perturbation. And in general, there are sharp features that carry direct information on the spectrum of the cloud that come in the form of resonances about the floating or kicked orbits, or the kinks in the evolution of the frequency I talked in the previous slide. So we didn't do generic waveform modeling because this needs to extend to eccentric orbits, inclined orbits, and introduce relativistic corrections. And also we are studying the interplay of resonances and ionization. Okay, thank you.
Thank you very much for the nice talk. We have time for questions. So you can raise your hand or post in the chat if you want. So there's one from Johannes. Go ahead.
Yeah, thank you very much for the nice talk. I was just trying to get some intuition, and I could probably work this out from the formula on one of the previous slides. When you have these kinks in the frequency, for what range of masses is this going to end up lying in the Lisa band? Like, what kind of mass range will be best constrainable with Lisa observations?
Yeah, so I guess this formula answers your question.
Mm-hmm.
For an intermediate mass ratio in spiral where the companion object is solar mass object. So,
sorry, I meant the mass that's, I guess, encoded in the alpha. So I guess the mass of the...
Oh, right. Correct, yeah. This would be around 10 to the minus 14 electron volts.
Okay, and plus minus a little bit, just I guess doing the scaling in my head. So I was 10 to the minus 14, you were saying electron volts plus minus what kind of range are we talking?
Well, it depends. Again, you can play with these numbers. So I'm saying 10 to the minus 14 because I'm taking the mass of the black hole equal to 10 to the 4 solar masses. And for a solar mass black hole, you have 10 to the minus 10, and it scales inversely. Mm-hmm. So it depends on the mass of the central black hole. You have to play with these two numbers. I would say plus or minus 1 order of magnitude.
Okay, that's perfect. Great. Thanks a lot, Giovanni.
Thanks.
Okay. If there is no other question, maybe I can ask one myself. Right. So you shown that you get very strong effects, I think, when dominating gravitational emission. What happens if you turn the problem around and ask what detecting normal-looking signals will give you as constraints? What kind of energy mass range can you exclude for like bosons in this way?
So sorry, can you repeat the first part of the question? You say I get a very strong effect, and
right. So if you turn this around, if we see a signal that is as expected, without any modifications, we can turn this into a constraint and exclude the existence of bosons in certain range. So what happens if you turn it in this way?
Right. So so it is somewhat tricky. I would say it's very easy to find you know, to recognize a detection, but it's easy to put an exclusion with this method because, for example, the cloud has a finite lifetime. The cloud is long-lived, but can, for example, decay if the scalar is a real field in gravitational wave and dissipate over a certain amount of time. So it depends if the in spiral happens before the cloud has dissipated, we're going to see this effect. But it's possible the boson is present in nature, the cloud dissipates, and then the spiral happens. In that case, we will not see the cloud. So it is a bit tricky.
Okay, I see.
It depends on the history of the system. I don't think there is an easy answer to that.
Okay. And there is another question from Samson.
Yeah, hello. Thank you for the talk. I have a very naive question. So since you're saying that it could be possible that you have a boson cloud around the central black hole, so could it happen that a companion also have a boson cloud around it? And then instead of having a gravitational atom, now you have a gravitational molecule? And if this effect is even observable, or do we need to care about this?
Oh, in fact, gravitational molecule is a term some people have used. However, superradiance is only efficient when these ratio scales, so say the mass, say the gravitational radius of the black hole to the Compton wavelength of the field is of order 1, right? So the same field cannot be responsible for superradiance if there's a large mass ratio. You need to plot 2 different fields in a large mass ratio scenario. What you said is, however, relevant if you have an equal mass ratio in spiral. In that case, the same field can be responsible for superradiance around both objects. And in fact, when the orbital separation becomes smaller than the radius of the clouds, you have what you said, a gravitational molecule, so a state around the orbiting binary.
I see.
But for technical reasons, we need the mass ratio to be large for our approximations to hold.
Right, it makes sense. Right. Thank you.
Okay, if there are no other questions, I think we can stop here. So we can thank all the speakers of the session. And we will have now a long break during which you are encouraged to look at pre-recorded talks and posters. And plenary sessions are going to start again in a bit less than 1.5 hours. So thank you all for attending today.